All right, so now that we know what these equations are and we have the Navier-Stokes equation, the problem is solving it. All right. So when we look at the equations, right, we have U, V, W, all right, and P. These are typically what we consider the dependent variables. And really, these three are the dependent, and we'd call this is a forcing function. All right, this is the, all right, in differential equations. And then we have X, Y, Z, and T. These are our independent variables, which means we have a very complicated equation. In fact, the Navier-Stokes equation is a nonlinear, because I have functions multiplied by themselves, second order, because I have squared derivatives or second order derivatives, all right, partial differential equation, all right, with lots of variables, all right, in particular with 4 independent variables that I need to solve for, all right. So we need to figure out ways to simplify this equation. All right, so I'm going to go over 2 ways to do it and then talk about a bunch of assumptions we use that make our lives easier. All right, so the first thing that we can do to simplify this equation, so to solve it, is do something called create a similarity variable. So in a similarity variable, in a very simple example, okay, we have an equation that looks like this: y equals x over t squared plus the cosine of the square root of t over x. All right, now this is, right, a 3-variable problem: x, y, and t. But what if I said, I'm going to create a new variable and say that x over t equals psi, then this equation becomes y equals psi squared plus the cosine of the square root of 1 over psi. And I go from 3 variables, right, to 2. So this is called creating a similarity variable, and it means that this is an easier problem to solve, and then I can always convert things back from psi to any particular x or t into a particular psi. All right, now we actually know how to do this because, well, we don't really know how to do this. Now, this is a hard thing to do. It's sort of an art form, all right? And you can use similarity solutions if you can, but in 2D, we actually have a handy-dandy thing, which is we have our stream function. So remember, we talked about the idea of a streamline, and we said that a streamline was a line that was tangent to the velocity everywhere. And so we're going to sort of create something that we call a stream, not line, but a stream function. Now, that's how it's going to end up, and we'll show how it's related to a streamline. But first, we're just going to do this, and we're going to see how we get there. So first of all, to note, this is only in 2D. And a stream function, we say that u equals d psi dx, and we're going to say that v equals d psi dy. So we're creating some new variable psi, minus, sorry. And we're going to say that its derivative in the x is u, and its derivative in the y is the opposite. The negative of its derivative is v. All right. So if we had a velocity vector v equals ui plus vj, we could easily now say that that is d psi dxi minus d psi dyj. And I've screwed something up already. And it's this. It's d psi dy minus d psi dx. All right, there we go. All right. So let's say I thought about the continuity equation, which says that in 2D for a fluid, an incompressible fluid, it looks like that. And I plug in these terms into that. What would I get? I would get d psi dx dy minus plus d dy of minus d psi dx, which automatically equals 0, because if I pull this term out, this becomes a minus, and this is a d psi, and dy dx. So if psi exists, it automatically satisfies the continuity equation, which means I don't even need to solve the continuity equation. Well, that's great. Okay. So psi does exist, all right? And what it is it's actually, if we think about streamlines from chapter 1, when we talked about streamlines, we had this idea dx over u equals dy over v. And so if you write out this a little bit, then you get u dy minus v dx equals 0. All right, and this is d psi dy times dy minus d psi dx times dx, okay? And that equals 0, okay? Except that because we had a minus here, we get a plus here because of the definitions of u and v, all right? Which means that what you end up with is d psi equals 0, or psi equals a constant along a streamline. So psi is a streamline, all right? So if we can create a flow that has streamlines, then we can think about a model for the streamlines. This is one way to solve it. Will you ever do this? No. All right. There's another similar thing where instead of stream functions, we use something called a potential function, where we say that v equals the gradient of phi. All right, so phi is our potential function, its gradient. And so instead of having, this means that we get u equals d phi dx, v equals d phi dy, and w equals d phi dz. So instead of having 3 velocities, we now just have phi. Again, it simplifies the problem, but will you use it? No, it's complicated. I'm not going to expect you to use it. All right. It's important to know the concept of a potential function, and it's important to know the concept of a stream function, but you'll never actually use them. All right, not in this class at least. So what do you need to know? There are a couple of key assumptions we are going to use all the time. All right, steady state. We've already talked about this before, but steady state says what? Any derivative d dt, doesn't matter what, equals 0. Okay, incompressible. Density is constant. Okay. We're going to use one that you've never heard of before. This is something called fully developed, and we'll talk about what it means more later, why it exists. But the idea of fully developed is it's, first of all, only for internal flows. That means flows in pipes. And what it means is that in the primary direction of flow, there are no velocity gradients. All right, so here's our example. Here's a pipe, all right, and I say the pipe has flow this way, okay, and what does that mean? So if this is my x direction, and this is, let's say it's a square pipe, so this is y, and this is z, okay? If my main flow is in the x direction, what I'm saying is that dv with a vector dx equals 0, or du dx equals 0, dv dx equals 0, and dw dx equals 0. Velocity does not change in the x direction. All right, so this one, fully developed, incompressible, all right, but fully developed, we use all the time for internal flows. All right, another one we're going to use is what we'll call a 2D assumption. That means, right, we're ignoring, and typically it means z, but we're ignoring one dimension. The way you might hear this said is that you might hear someone say that this particular dimension, let's say, in the z direction, so we have some length scale Lz, is much, much bigger than Lx or Ly. And what we're saying is that in the z direction, this thing is basically infinite, and so we don't care about gradients in that direction. We're going to ignore everything in the z direction. It does not matter. Okay? So those are really useful. because all of these, you can see, get rid of certain terms in our equations and will make them easier to solve. And I'll show you how to do that.